Okay, so we're kind of back in the grind now. Last week we got together, we talked about work energy for individual particles. So we set up work expression, or work energy. We said T1 plus V1 plus the work between the 1 and 2 is equal to T2 and V2. So this is where we were last week. Today we're just going to build off this a little bit by not considering just one particle, but considering a system of particles. So just as a quick trip down memory lane, T is what we called kinetic energy, half m velocity squared. Our V terms we had for a spring, half k, the spring constant, times its displacement squared. And we had potential from gravity, mgh, mass times gravity times the change in height. And our work between 1 and 2, this was the integral of our forces dotted with their displacements. So remember our potential energy terms we plucked from this work term. So we said this was U12 NC, non-conservative. So we left some things in there. We left like a pulling or pushing force. We left friction. But we pulled out some of these guys that we see all the time, where the forces aren't path dependent. So the independent of path, conservative forces, we pulled those out. So what are we going to do? We're going to add some complexity by not just looking at a single particle, but looking at the interaction between multiple particles or a system of bodies. So we did this really similar thing in chapter 3, where we were looking at sum of forces over a single particle, and then we added two particles. And we looked at sum of forces over both those particles. Same thing we're doing here. So if we have multiple particles, in our system now, we've got some internal forces acting on these. So F12 between particles 1 and 2, F13 between particles 1 and 3, F23 between those guys. So remember these forces, equal and opposite. So when we were doing our sum of forces over a system of particles, these guys just came out in the wash because I added one and then I subtracted the other. So in the end, I didn't care. Today, the story's going to be a little different. We're going to care. So remember, for this, we can have internal forces, but there's no reason that we still couldn't have external forces. Acting on our system. So when we go do our sum of forces from this, equals mass times acceleration. That's our Newton's second law. We're going to have a summation over I equals 1 to n particles of our external forces plus a summation over the internal forces. Actually, I can go, I didn't make these guys lowercase, but I'm going to make them lowercase in my figure now. So external forces, internal forces equal to the masses times the accelerations. All right. So if this is what we had for our Newton's second law, To get to work energy, what we want to do is we want to integrate this over our displacements. So we integrate from state 1 to state 2 of this whole thing dotted with dr. Right, that's just the definition of how we got to work energy. We started with F equals ma. We integrated along our path. So a lot of this is going to be old news. The integral of mass times acceleration dotted with dr, that's just going to end up being a summation of our kinetic energies. Our external forces dotted with dr, that's going to be our work between states 1 and 2. I'm going to put external on here. So that one's kind of the same. This new guy, we have to account for. We've got this double sum now of our internal forces dotted with dr. This is the integral between states 1 and 2. So this guy, internal forces acting over some distance, we're going to call this U12 internal, INT. So everything we did before still applies. For my external work, we could pluck out our potential from springs, our potential from gravity, just like we did in the past. But now we have to track them over multiple particles. So if I've got 2 particles, I got to figure out how far particle 1 has moved up and down. But then I also have to figure out how particle 2 has moved up and down. So these are really more our summations of our potentials over all the particles. This guy, that's a little bit new for us. That's all the same stuff. So our work between state 1 and 2. Our internal work between states 1 and 2. We've got, again, this double sum, I equals 1 to n, j equals 1 to n, of our integral, f sub ij dotted with dr. In general, it's not going to be 0. So when do we need to keep track of this? This is what we're going to spend some time on today. Sometimes the internal work will be 0, and we'll talk about that, but sometimes we actually have to account for it. So the first one we're going to look at, ropes and cables. So for the most part, in this class, whenever we have ropes and cables, we always talk about them being inextensible. So inextensible, they don't change their length. If they change their length, then we usually account for them as a spring. So if our ropes and cables don't have a length change, what do these internal forces look like, and how does that internal work behave? That's our job. So if I've got block A attached to block B, here's our ground, and I'm pulling on block B. I'm going to move block B some bit, XB. Well, if this cable is inextensible, in this case, XB is going to be equal to XA. As I drag B along, A just comes along for the ride. So if I draw my free body diagram of these guys, I've got a tension acting on A and B. It's my internal force from this cable. Obviously, we still got some friction on the ground. We've got normal forces from the ground. We've got weight coming down. But I want to look at the work being done by my ropes and cables. So I'm only going to pay attention to this internal force right now, just to make my free body diagram a little simpler. So if I want to take a look at this, I say, hey, what is my internal work? All right, well, I want to look at both pieces. I've got the integral of force dotted with their displacements. So to make life a little bit easier, let's assume that t is constant for now. So if my force is constant, then when I'm integrating that over displacement, it can just become a multiplication. So for particle A, I've got t in the I direction dotted with xa in the I direction. That's our first piece. And then our second piece, the internal work from our second one. So B, oh, now I got minus t in the I direction because it's pointing in the negative, dotted with xb in the I direction. So this is my internal work from the cable on B. Here we said that A and B, as I'm pulling them along, travel together. So I'm going to get rid of this xb and call this xa. Those guys are linked. My dot products, I with itself, those will just go to 1. So my internal work here, txa, and then minus txa. Zero. So in the case where I have ropes connecting these blocks together, and they're inextensible, however much I'm pulling on one rope and moving something, that force is going to be kind of equal and opposite the direction we're sliding. So the work ends up being 0 altogether for our ropes. If we made this problem a little more complicated, we're going to get the same result. So if I went, I've got A here, and now I've got B on a pulley. We can use this same thought process to work our way through it. I'm going to look at how far A is gone relative to how far B is gone. Hey, we could do this kind of the way we have in the past, where I could write a rope equation. Maybe I would say that this is SA, in this distance SB. And I could figure out that as I pull B 1 unit, A is going to move a half a unit, right? Or if you want to think of it the other way, as I move A 1 unit, B is able to move 2 units because it's got a pulley acting on it. So if you'd like to, you could write the rope equation. If not, I'm trying to do this kind of the quick and easy way. So my FBD at A would look like T and another T. So 2T acting on A. And on B, I've got a T going the other way. If we're thinking about work, though, I want to know force dotted with displacement, or the integral. In this case, if these T's are constant, force times displacement. So for my internal here, if I look at A first, I've got 2T in the I direction, dotted with XA in the I direction, assuming positive to the right. Plus what I've got for B, minus T in the I direction, it's going the other way, and B is now going to go XB in the I direction, or 2 times XA, because it's on a single chord and the other one's on a double. So what do you get? 2T XA minus 2T XA. You can go ahead and make this as fancy as you want. Add 3 pulleys, add another one, add another block or 2. But you're always going to come to the same conclusion. Hey, if I've got a pulley and I'm pulling on it with some force and I'm trying to lift that object, no matter how many strings are attached to that object, how many pulleys I have set up, the work I do on one end of that rope is going to be the same as the work I do on the other end of that rope. Now, you got some kind of crazy system where, I don't know, there's this like 10T, and then there's something happening and that's coming over to me, and I'm just pulling with 1T. Perfect drawing. We're doing the same amount of work. So if I'm only pulling with 1T, I got to pull 10 times further than this guy can move, right? For that work to be the same. So work is force times displacement. If here I've got 10 times the force than I do over here, here I got to pull 10 times as far as I do to move this. And that's how we move things with pulleys, right? Like, hey, I'm only 1T strong, but I'm super patient. I can sit there all day and pull. And eventually I can lift up something super heavy. And that's what we're going to see here. So whenever you have a problem and you start looking at these, you start drawing your free body diagrams, you've got tension and tension, and you can certainly include these in your internal work calculation. Nothing wrong with that. Just at the end, you better come to the fact that one cancels the other one out. Otherwise, you're going to be in a little bit of trouble. So I just told you when you don't care. When do you care? Internal friction. So for friction, you've got some relative motion happening between the two objects. So maybe I initially start here. These guys are sliding. And in the end, they look like this. A is moved more than B. So here, this is my XB. This is my XA. I got some relative motion between these blocks. I've got some friction happening on this surface. Whenever you think like, hey, there's friction as these blocks slide, friction is like stealing energy, right? It's just gobbling it up. So that's the part we want to keep an eye on. If we look at our free body diagram, let's take one of the systems and kind of break it apart, see everything we have. So on A, I've got our weight coming down. I've got my normal force between the blocks. That's an internal force, so I'm just going to steal it again and write that on B. B's got a weight coming down. B has got a normal force pushing up. And then I got some friction. Okay, when we think about friction, we think about relative motion. Whenever I think about relative motion, I say, hey, what does it look like A is doing if I'm on B? So if I sit here and I kind of squeeze B so it can't slide anywhere, A looks as if it is moving to the right. Right? A is moved to our right relative to B. So for that one, my frictional force opposes that relative motion, points backwards. My other internal force better be equal and opposite that direction. So I just write it in the other way. So if I took this free body diagram and I squeeze these two pieces back together, these internal force from the normal, internal force from FAB would cancel out. All right. What I'm interested in right now, though, internal friction. So these guys are the ones we want to chase. Our frictional force between A and B. Here we're going to assume kinetic friction. There's some sliding happening. So mu K times the normal, NAB. If we wanted to get fancy, I could do sum of forces in the y direction to find out what MAB is, but I'm also a great inspector. I can just do that by inspection. So we've got our frictional force. I want to figure out the work. This frictional force, mu K, Ma, G, all constant values. So even though our internal work is going to be the integral dotted with displacement, in this case, it's a constant force. So we can just have our force multiplied by our displacement. So on block A here, I've got negative FAB in the I direction. It's pointing in the opposite. That's going to be dotted with the displacement of A. XA in the I direction. Then I've got B here. FAB is in the positive direction. And its displacement, XB. So for our dot products, I dotted with I, again, that's just going to be a scalar 1. So these guys will fall out. Our internal work, minus FAB XA plus FAB XB. Rewrite this in a little easier to understand. So our work is FAB times XB minus XA. Hey, this is something that we've seen before. Here, we set up relative displacement equations. Relative velocity equations, relative acceleration equations. This, XB minus XA, that's the displacement of A relative to B, or of B relative to A, sorry. So this is equal to FAB times the displacement of B relative to A. Or I think maybe a little easier in this case, remember the displacement of B relative to A is opposite of the displacement of A relative to B. So our internal work is equal to opposite of the frictional force times displacement of A relative to B. A relative to B, if I can try to sneak all this on to one slide, this is how far A moved. Box A slid this much. Compare that to box B. That's just A and B. So this would be A relative to B is moved that much. So our internal work from friction, we might not necessarily have to know how far A is gone, how far B is gone, but all we need to really track is how far they move relative to each other. So we have how long is that internal friction working? And it's working on this distance, A with respect to B. So we'll do an example, hopefully, that'll make that pretty clear. Okay, to sum up, we still got our same old work energy. T1, V1, plus our work, non-conservative, a lot of scripts here, external. Just making a differentiation between internal and external work. Plus now I've got this work between states 1 and 2, internal, is equal to T2 plus V2. This is kind of a shorthand, lazy way of writing this, right? Because really this T1 is a summation over particles, I equals 1 to n, of the various Ti sub 1s, right? If we've got two particles, it's like half m1 v1 squared plus half m2 v2 squared plus however many particles you have. This is maybe a bad notation. So let me jump in real quick. I said v1 because it's state 1, but I've got multiple particles. So maybe for my particles, 1 sub 1, particle 1, state 1, particle 2, state 1. Do we follow that? Maybe I should have used A's and B's, but then I got a summation over A's and B's, and I didn't like that. So sorry, this is kind of funny notation. The point is, track the kinetic energy for every particle you care about. Track the potential energy for every particle you care about. So for gravity, m1g h1 sub 1 plus m2g h2 sub 1. Track the height positions for all these different particles. In a case like this, where you're tracking different heights, you can use different datums. So you can use a datum for piece 1 and a datum for piece 2. As long as you're keeping track of their relative motion between state 1 and state 2, you're going to be just fine. Okay? So this work could be external work from friction. You might have a motor. We might have a rope being pulled or someone pushing something. This internal work between states 1 and 2, again, the work from cables, gone. If we had internal friction, though, that's kind of that one thing that we're going to be keeping our eye on. So here's the problem that looks just like what we drew. The truck and a crate come to a stop under the action of a constant braking force applied to the truck. Does the truck stop in a shorter distance if the crate slides forward as the truck stops, or if the crate does not slide? So, two cases. We're slowing the truck down in a shorter distance if the crate is allowed to slide, or if the crate is not allowed to slide. So as a trucker, maybe you think, do I really want to crank this crate down all that much? Well, the answer is probably yes, but can I stop in a shorter distance? Immediately, get the wheels turning. What's happening here? If this crate is sliding relative to the truck, there's some internal work, right? There's some friction happening as this crate slides over this 20 feet in this drawing, right? So as that crate is sliding, that's friction, and it's stealing work from the system. So if this friction is stealing energy from the system, hey, that's just helping us out. We're going to be allowed to brake in a shorter distance because the amount of energy that we're trying to slow down, half mv1 squared, is going to be less, right? I have another thing helping me slow down as opposed to braking. I'm also stealing energy from our frictional loss. But let's try to show that. All right, So with work energy, we'll start out with our full size equation. Kinetic energy at state 1, potential energy at state 1. External work, internal work is all equal to the kinetic energy at state 2 and the potential energy at state 2. We just want to figure out what our braking distance is. So maybe what we care about, XB. How long does it take this truck to stop, right? So this problem, life can be a little bit easy for us. Initially, we have some velocity. So we have a T1. Half mass of our truck, B, times the velocity of our truck, B, squared, at state 1, plus the other component, half mass of my crate A, velocity of A, at state 1, squared. So our two kinetic energies, at state 1, they're moving together, though. The crate is happily sitting on the back of the truck. They're moving at the same velocity. So these guys are equal. So this can simplify to half ma plus mb, velocity of b1 squared. That's how much we're slowing down. Or that's how fast we're initially going. We think about our potential energy terms, v1 and v2. Well, if you look at this problem, we're not going to assume we're storing any energy in springs because we don't see any springs here. And the height of our crate and the height of our truck are constant throughout the entire braking process. So life gets a little bit easier for us. We're canceling out potential energy changes. No springs, no height change. T2, we're coming to a stop. At that stop, we're assuming both the truck and the crate have stopped. So zero velocity, that one falls out. Now this is looking pretty promising. We've got a bunch of terms that have canceled. So let's go after our external work. Our external work, the integral from state 1 to state 2 of our external forces dotted with their displacements. Well, we're told that it's got a constant braking force. So FB, the only external force acting in this x direction, that one's going to be constant. So again, this integral becomes a multiplication of force times displacement. So my external force is minus my force of braking. Right? If I'm slowing this guy down, you could think of the braking force at the wheels slowing us down. So that's in the minus x direction. If I choose kind of our traditional xy system, xj system, we'll deal with that. Dotted with our displacement. So how far the truck has moved because the braking force is acting on the truck. It's moving to the right in this problem. So again, I dotted with I goes to 1. So we're just left with minus our braking force times that braking distance. If you wanted to say, like, hey, what's case 1 with it not sliding? You could do this. You could just say T1 plus U external is equal to 0. Here we're going to assume no sliding. So their internal force is 0. Okay? If you did that, you could solve for XB. because I've got my T1 and I've got XB here. So XB is MA plus MB VB1 squared over 2 times my braking force, FB. And again, this is for the case of no sliding. Hopefully this wasn't too magical when I made this jump. All I did was take our T1 that we had, plugged it in here. My external non-conservative work minus FB, I plugged it in here. So these guys, I set them equal to each other, or 1 plus the other equals 0, and solved them. But now we've got sliding. So our internal work not equal to 0 anymore. Not so lucky. Well, we just went through that explanation of what it looks like. A to B goes to something like this, right? A is slid relative to B. Kind of exactly the drawing we just did. So our internal, we just decided that was our frictional force between A and B. Multiplied by the displacement of A relative to B. And in this case, because A is sliding to the right relative to B, our frictional force was in the negative I direction. So I just did what we did where we started our last, or ended our last problem. But you certainly could have said on A, if I would have drawn this out, I've got a frictional force. On B, I got that opposite frictional force. You could have plugged them in. Frictional force times the displacement of A. Frictional force times the displacement of B. But this is where we got to, right? So minus the frictional force between A and B, x of A relative to B. Now we can jump back. T1 plus V1 we said was 0. External non-conservative. Plus internal non-conservative is equal to 0. So my T1 half mass of A plus the mass of B times the initial velocity squared, plus our work, minus our braking force, our external work, times how far the truck has gone, and our frictional part, minus F AB of x of A relative to B equal to 0. In the end, I want to figure out XB. I could have swapped this term out, x of A relative to B, subbed in for a XA minus XB. Doesn't really get me anything in the end. I still have to know that distance it slid. So in the end, I get that XB is equal to our same term from before, MA plus MB VB1 squared over 2 times my braking force, minus this extra little guy. FAB of x of A relative to B. So this is like our sliding correction factor. And in this case, as long as A is greater than B, it's going to have some negative effect because our friction is going to oppose that motion, and our sliding distance is going to be that much shorter. So just a little correction factor if you are allowing that crate to slide. So maybe your crate's really, really big and your truck is really, really long, then you could have a whole bunch of effect of energy loss due to frictional sliding. Maybe your truck has a driver you care about and you really don't want that crate to slide and smash into the front of it and hurt them, right? So while this isn't a terribly practical way to slow your truck down faster, it is, for this case, interesting to see how we can transfer energy and kinetic energy and work done internally.
Would the sliding part also be divided by FD?
Yeah, I had that the whole time. Thank you. So, yeah, I just missed that, right? As I'm moving things to the other side, this guy over, and then divided both sides by FB. Thank you. My notes were right. I just messed it up. All right. One more example just so everyone leaves happy and fulfilled. Here we've got two crates. I got a block A and a block B. Block A weighs 60 pounds. Block B is a little guy, only weighs 10 pounds. And we have a kinetic friction coefficient between the incline and block A, so it's sliding here, of 0.2. We're going to neglect the mass of the cord and the pulleys and any friction around the pulleys. So determine the total work done on system AB as block A moves 3 feet down the incline. So block A is going down 3 feet. So immediately you see block A going down 3 feet, and I think, what's block B doing? It's attached to a pulley. And then you can write this out by hand. You can do your rope equation. You can take your derivative, set it equal to 0, and see how much one's velocity moves with respect to the other. Or you can just come in here with your engineering eyeballs and say, hey, block A, 2 ropes attached to it. Block B, 1. So if block A, we know that internal work between the two systems has to be equal. The tension done as block A is sliding 3 feet, it's got 2 tensions, so that's going to be block B with 1 tension sliding double that, right? So block B is going to be going up 6 feet. And I'm not looking at the masses of these different blocks, seeing that one's 60 pounds and one's 10 pounds. I'm only looking at that tension. I want to know, how is that tension's work being done on these two pieces? So the tension is going to do work as a force times the distance. In this case, the tension on A is moving 3 feet, but there's 2 tensions. On block B, that tension is only 1 cable, so it's got to be moving double. So it's moving 6 feet. We want to figure out the total work. So what is this going to look like? Total work between 1 and 2. So maybe we'll write it like T1 plus U total, 1 to 2, is equal to T2. For us, work done from potential energy, springs, and in this case, gravity, that's still work being done to a system, right? We've taken those and we've pulled those out as potential energy terms. But if someone's asking me, hey, what's the total work being done? Then I want to leave them in there because that is a work, just a work done on potential. So this problem, we don't even really know anything about T1 and T2. We're not asked anything. We don't really need it. We just need to figure out what's all happening in our work. So our total work we can think of this as our change in potential energy plus our external work between states 1 and 2 plus our internal work between states 1 and 2. And I guess I always said non-conservative, right? Because the conservative parts I pulled out as potential energy terms. Maybe the interesting thing is to just go through here and say, like, what bins do these different terms fall into? So, potential energy, springs and gravity. I don't see any springs, so we just have a gravity term to track. This autofocus is killing me today. Okay. All right. Sorry. The external work from non-conservative forces. Now you think, what's acting on these bodies from the outside? That's going to be our friction on the incline. Internal work between states 1 and 2. What are we interested in? Well, the internal forces between these two blocks, the only thing between them is the cable tension. There's no internal friction on this system between the two blocks because they're not touching each other, sliding relative to one another, right? So if this is just cable tension, pew, 0. Really, all we got to figure out now, gravity, how much these things have moved up and down, and our friction on the incline to figure out the work being done on block A. So gravity is the easy one. So the change in our potential energy, this could be our potential from gravity at state 1 minus our potential from gravity at state 2. Time to pick some datum points. For me, I want one side to be 0. So I start my datum there. And I'm going to do these guys relative to their positions. So I can go like this. I can say, hey, this is my datum for A. This is my datum for B. And I just want to see how far they move relative to each other. So this is M A times G times, call it YA2, plus MBG YB2. And this is the opposite of that because my change in potential, negative. So go ahead. We're told in the problem statement how far A has moved down. It's moved down this hill 3 feet. Well, there's a triangle there, so you've got to figure out how much that is actually changing in its position in Y. So my AY2 is going to be 3 feet times some ratio. Looks like 3 over 5, based on the shape of that triangle. B, how much is B moved? Hey, I already got it on the screen, right? 6 feet. So that one, MBG times 6 feet. The other thing we need to do is figuring out the internal friction. To do that, I need to draw FBD of A, figure out the normal force, figure out mg coming down, and then I can figure out how far it's gone. So I will finish that up and post that for you guys, and then I'll see you on Thursday.